All right, welcome back to Calculus for Economics. I wanted to follow up the video that I posted earlier today with a second one in which we look at another optimization problem. This will be a little bit more involved than the first one, but not too much. So I hope it will help you as you start working the homework on this topic. So yeah, let's get right to it. The problem I want to consider today or now has as its goal minimizing cost. Previous problem we wanted to maximize an area. Now we want to minimize cost. But it's kind of similar in a certain sense. Basically, I'm imagining a pasture here that's adjacent to a river. And I want to fence in 200,000 square feet of that pasture. So that's a pretty healthy sized chunk there. But there are some costs associated with that. The fencing for these two sides here, the sides that are adjacent to the river, cost less than the fencing on the front part of the pasture. And this may be because, maybe there's a road going past the pasture over here, and the owner wants to make the fencing over here a little bit more, pleasant to look at or whatever. And so here are the details. We want to fence in a pasture adjacent to a river. We must enclose 200,000 square feet in area here. Fencing for the two sides adjacent to the river costs $6 per linear foot, while fencing for the other side, the front side here, costs $10 per foot. And so what are the dimensions of the pasture that cost the least to fence? So that's the question. You might say, well, we'd want to minimize the amount on the front side, right? And so make that as small as possible. But you obviously couldn't make that zero. You couldn't have no fencing on the front, because then you wouldn't have a pasture at all, right? You would enclose 0 square feet. We've got to enclose 200,000 square feet. So we want to be able to do that, and yet, in essence, use as little on the front as possible. So the question is, how can we do that? So let's see what we can do here. Let's get started. And you may remember from the previous video that I had suggested that one of the ways to get started on something like this is to just, take it easy, identify your variables first, and then identify the objective, and that's what the objective function here will do for us. And then identify the constraints you have to work with. And so let's do that. Similarly to the last example, let's label the sides of our pasture here. So the two sides, adjacent to the river, we'll call X again, and the side Y here on the front side we'll call Y. Of course, I don't need any fencing adjacent to the river. I'm assuming that the river itself is going to act as the boundary there. And so there won't be any fencing back there. So let's just label these. X will be the side length, and that's going to be in feet. Y will be the front length, again in feet. So those two things obviously are important. But what we're trying to do here, you remember, is minimize cost. So cost is clearly a variable as well. I'll just use capital C to be the total cost of fencing this pasture. Okay, now what we were told was that the fencing for the front was $10 per foot, while the fencing for the sides was $6. So I'm just going to make that notation up there. And that's going to be important in putting together our objective function. Our objective function is the cost, right? So what would be the cost of building this fence, and I'm ignoring labor costs, by the way, but what would just be the cost of the fencing itself if I had these dimensions, x on the sides, y on the front? Well, to fence the two sides, I would have, like to fence this side here, I have x feet, and then it's $6 per foot, so it would cost 6x in order to fence that side, and obviously it would cost 6x to fence the other side as well. And then for the front, I have y feet, and it's the fencing is $10 per foot, so I'd have 10y. So that would come down to what? 6x plus 6x, or 12x plus 10y would be our objective function. The objective function gives us the function that we're trying to either maximize or minimize, and that's what we have here. What about the constraint? Well, the constraint was that we had 200,000 square feet in the fenced-in area. So I'm just going to write that as 2 times 10 to the 5th to just help eliminate writing a bunch of zeros. That's 2 with 5 zeros following it, right? So the constraint would be that x times y, the area of this rectangle, would equal 200,000. X times y equals 2 times 10 to the 5th. And there we have the basics of the problem sort of translated into mathematical language. So now the question is, we've got a mathematical problem, how do we solve it? So what do we want to do? We want to minimize C. So that's our goal. Well, you see in this cost function now the same kind of issue we saw in our previous example about making a rectangular garden. That is, this is a function of 2 variables, and I know how to do calculus with 1 variable. So the technique here is to use the constraint to solve for 1 variable in terms of the other. So for instance, the constraint here says that x times y is 200,000. From the constraint, I see that I can solve for y in terms of x. So y would be 200,000 divided by x. And that way we can then plug that back into C, and you get a function of 1 variable. So C would be 12x plus 10 times y, but that'd be 10 times 2 times 10 to the 5th over x. Or if I can just simplify that a little bit, C would be 12x plus 2 times 10 to the 6th power over x, right? And so that's our objective function, now written as a function of x alone. So now we want to minimize that. So the procedure here would be to find critical points, use the second derivative test to make sure you got a maximum or a minimum, or to figure out whether you have a maximum or a minimum, and so on. So critical points, those are places where C prime is equal to 0 or C prime is undefined. So C prime here, and I'm just working off this, would be 12 plus, and if I think of this as 2 times 10 to the 6 times x to the negative 1 power, I would have 2 times 10 to the 6th times the derivative of x to the negative 1, which would be negative 1 x to the negative 2, or I get 12 minus 2 times 10 to the 6th over x squared. That's my derivative. Okay, so let's look at places where the derivative is equal to 0. C prime would be 0. So I'm just going to set that guy equal to 0. So I'd get, let me first multiply through by x squared, right? So I'd get 12x squared minus 2 times 10 to the 6th equals 0. But that would mean that 12x squared equals 2 times 10 to the 6th. And that would mean that x squared would equal 2 times 10 to the 6th over 12. And then if I take the square root of both sides, so raise both sides to the 1/2 power, I'll get x would equal, what would it be? I'll have this, I can just get a 6 in the denominator there, and then I would have the square root of 10 to the 6th, that's 10 to the 3rd, divided by the square root of 6, and I can just leave it like that. So that's 1,000 over the square root of 6. That's my critical point. Now, I should mention here at this point that critical points also include the cases of points in the domain of the function where the derivative is undefined. Now, if you look at our derivative here, it's 12 minus 2 times 10 to the 6 over x squared. You see that that derivative is undefined when x equals 0. But the point is, x equals 0 isn't in the domain of the function either, right? Here's c. So x equals 0 is not in the domain of the function. So even though the derivative is undefined when x is 0, it's not a critical point in this case because a critical point has to be in the domain of the original function. And x equals 0 is not in the domain of our original function c here. So x equal 1,000 over radical 6 is our only critical point. Does it provide a maximum or a minimum? Well, there's where we want to look at the second derivative. The second derivative test tells us whether we've got a maximum or a minimum. So if we look at c double prime, that's going to be the derivative of my c prime, this guy right here. And so the derivative of 12 is 0, and then we would get minus 2 times 10 to the 6th times the derivative of x to the minus 2, right? So that would be minus 2x to the minus 3. And so that's equal to what? 4 times 10 to the 6, because minus 2 times minus 2 is 4. And then times x to the minus 3rd, or just divided by x cubed. So you can see that the second derivative is going to be positive for our critical point, because our critical point is positive, and then you're just taking one positive number and dividing it by another one. So that is positive. So now what do we know? And again, here's where you want to put together ideas of concavity as well as horizontal tangent lines. We've got a horizontal tangent line at x equal 1,000 over radical 6, and our graph is concave up. So what can that look like? You've got a horizontal tangent line, and you got a graph that's concave up. You've got to be at a minimum, right? So that tells us that x equals 1,000 over radical 6 provides a relative minimum for the cost function c. And 1,000 over radical 6 is, I'm just popping that out of my calculator real quick, 1,000 divided by 6 raised to the 0.5, about 408.25. So what we would need to do here is fence in about 408 1/4 feet on each of these sides. And then what would the Y value be? Again, how much would you need on the front end here? Well, remember our Y is related to X through that equation. And so if I plug that in, actually I already worked that out a little bit. It turns out that Y is going to be, so I'm leaving out a little bit of work here, but it turns out to be 2 times radical 6 times 10 squared, and that turns out to be 489.90. So you need almost 490 feet on the front and a little bit more than 408 feet on each side. And if you go ahead and multiply X times Y together here, you will find that X times Y is 200,000. So our constraint would be satisfied here. A couple of ending thoughts here. First of all, WebAssign, I think, would probably prefer you to go ahead and give the answer in the original form as 1,000 over radical 6. I'm not exactly sure if it would have taken the 408.25, since that's a rounded figure, and he typically prefers exact numbers. So if you can give the number exactly, like in terms of square roots and so on, you should. You could also you could find out, well, how much is this whole thing going to cost? You could find out what the minimum possible cost is just by plugging these X and Y values back into your original objective function, right? Because that function tells you what the cost is when you use X feet on the sides and Y feet in the front. So there you have it. That's our second applied optimization example. So you ought to be ready now for the homework that's due on Wednesday on this topic, and I think there's 3 problems on that. They all require a little bit of thought, so be patient and give yourself a little time to puzzle through these. They're not easy. Let me know if you have questions, and stay well, stay in touch, and I will be back in touch with you very shortly. Y'all take care now.